right, guys. So for this video, we're going to start looking at graphing rational functions. And we're not actually going to graph them yet, but we're going to look at 5 different key features that you can all get without using a calculator, without even looking at the graph. It all comes from the equation. All right, those 5 things are going to be our x-intercept, our y-intercept, vertical asymptotes, horizontal asymptotes, and holes. All right, so for our x-intercept, we'll talk about shortcuts in just a second, but the long way of finding your x-intercept, anytime you ever want to find the x-intercept, is going to be to plug in 0 for y. Because no matter where or what kind of equation you have, if you are on your x-axis, if it's an x-intercept, you're going to have a 0 for y, like 4, 0, -2, 0. So no matter where you are on the x-axis, y is always 0. And then likewise, if I want to find my y-intercept, I'm going to plug in 0 for x. And what I mean by plug in 0 is replace all of the x's with 0 and then see what y equals, right? Or plug in all of the y's, put in a 0 and see what x equals. All right, so that's our long way. And again, we have a shortcut we'll look at in just a second. Okay, your vertical asymptotes, all right, is anything that makes your function undefined, all right, or it's values that x cannot be. All right, anything that makes your function undefined, right? That's a big word. Remember, we kind of talked about this with our solving equations where we can't divide by 0, right? Or that makes your function undefined. All right, your horizontal asymptotes, or asymptote, is going to be values that y can't be necessarily. It's not the best definition because technically it could still cross a horizontal asymptote. Really, your horizontal asymptote is looking at your end behavior. All right, so it's looking to see what your graph is doing on either end. It's going to be approaching the horizontal asymptote if it has one. All right, and then holes is a function or part of the function where it's still undefined, that undefined word coming back in there. All right, but it's not a vertical asymptote. So it's still something where your function is undefined, but it's not going to be something that your graph approaches. It's literally a hole in the graph. And when we graph it, you have like your curve coming up, and then there's literally a hole. And then your curve keeps going. So it's not going to be a dotted line, but it's the same kind of idea. It's still where your function is undefined. All right, but we do have shortcuts. All right, so if you remember, these rational functions are fractions. Okay, so like for example, if I, let's just make up an example. If I have 1 over x plus 2, right? Oh, that's gross, but y equals 1 over x plus 2. So for my x-intercept, right, I'm going to plug in 0 for y. So in this case, I'm going to have 0 equals 1 over x plus 2. And I hate this example. I changed my mind. This is terrible. I should have written this down first. We're going to make it x plus 1. Oop. Over x plus 2. There we go. That's a little better. All right. So if I plug in 0 for y and solve for x, you can never ever solve for x if it's in the denominator. So the first thing that we have to do is multiply by that entire x plus 2 to get it out of the denominator. Right? But if I take anything times 0, my answer is 0. So this ends up going away altogether, and I'm left with 0 equals x plus 1. Right? Then if I solve for x, I can subtract 1, and we get 0 equals -1. So for this example, right, my x-intercept is at -1, 0. But this process happens every time. If I set my function equal to 0 by plugging in 0 for y, I'm going to have to multiply by the denominator. And when I multiply by the denominator, it's going to go away because it multiplies by 0. So my shortcut, every single time I want to find the x-intercept, is just to set the numerator equal to 0. All right, so that's your shortcut. That's what you got to remember. If I want to find my x-intercept, I can set the numerator equal to 0 every time. Okay, for the y-intercept, we end up with a similar shortcut. Y-intercept is a little bit easier because usually it's always y equals and then you have a bunch of x's. So if I were to plug in 0 for x, I end up with 0 plus 1 over 0 plus 2, which ends up just being y equals 1/2, right? Everything that has an x is going to go away, right? If that was x squared, 0 squared is still 0. If that was a 5x, 5 times 0 is still 0. So every term that has an x ends up going away, and you're always going to be left with whatever's on the end without an x. So my shortcut for the, get my star on there, for the y-intercept is just to divide the constants. Every time, whatever my constants are at the end, we're going to divide, and that's going to give me my y-intercept. If there isn't a constant, that means your constant is 0. So just keep that in mind, and we'll see one of those in a little bit. Okay, your vertical asymptote is anything that makes your function undefined, and we talked about this when we solved. Your function's undefined if you divide by 0, because you can never, ever divide by 0, right? So my shortcut for the vertical asymptote is always going to be whatever makes my denominator equal to 0. All right, anything that makes the denominator equal to 0 is going to be a vertical asymptote. All right, our horizontal asymptote, we have a buddy that we turn to. We turn to our buddy Bobo. All right, and it sounds silly. All right, but we've got Bobo, Botan, Spud. All right, we got to turn to our buddy Bobo. He tells us everything we need to know about our horizontal asymptote. So what Bobo stands for, let me change colors. All right, you have 3 scenarios when it comes to these rational functions. Your first scenario stands for bigger on bottom. All right, and this is talking about your exponents. So bigger on bottom. All right, if you have a bigger exponent on the bottom of your fraction, right, that means that your asymptote is 0. All right, so you have a horizontal asymptote at 0, which is your x-axis. All right, Botan stands for bigger on top. All right, so if you have a bigger exponent on top, then there is no horizontal asymptotes, none. And then SPUD, Spud, same power. U, the letter U, divide. All right, so same power, you divide. Now, what do you divide? You divide the coefficients. All right, now that's another C word. That's often the common mistake, is mixing up coefficients with constants. But if it's a horizontal asymptote, you're worrying about the stuff out in the beginning, right? Because you're looking at whatever your biggest exponent is, which is going to come from your first term, right? If it's in standard form. And you're looking, if it's the same power, same exponent, then you're looking at the number out in front, your coefficients. All right, so let's look at the asymptotes for this example I made up. Okay, so I have x plus 1 over x plus 2. So for my vertical asymptote, all I care about is the x plus 2, my denominator. So we could say x plus 2 equals 0. Subtract 2 from both sides. So that means I have a vertical asymptote at x equals 2. All right, so when it comes time to graph that, that means I can find -2 on my x-axis and put a dotted line, a vertical asymptote. All right, so that's when it comes to graphing. Right now, all we're doing is finding these key features. Okay, for the horizontal asymptote, right, Bobo, Botan, Spud, it's got to be one of these 3. Either it's going to be bigger on bottom, bigger on top, or it's going to be the same power. So if I come here, I have x, let's see, x to the first power over x to the first power. So that means for this example, we got Spud, right? Same power. So if it's the same power, we're going to divide the coefficients. Well, in front of the x here, there's nothing, which means that it's really a 1. And on the bottom, same thing, there's really a 1 in front. So if I'm going to divide my coefficients, right, my horizontal is always y, right, equals 1 over 1, all right, which is just 1. So that means for this example, I have a horizontal asymptote at 1. Okay, so now if I were to graph that, I would go to 1 on the y-axis and put a horizontal line. All right, so you're only looking at your first terms, your highest exponent on top and on bottom, and it's either going to be bigger on the bottom, bigger on the top, or the same. So Bobo, Bot, Spud. All right, and for holes, okay, holes are kind of weird. They're not as common, right? You don't, most of the functions, especially the ones that we look at, are going to not have holes, right? But they could, okay? And the way that you see if there's a hole, right? For all of these problems, we're going to be factoring. Okay, so what you do is you factor and you cancel anything, just like we simplified our rational expressions before. So factor the top, factor the bottom, cancel anything, simplify it as much as you can. All right, your holes come from anything that cancels. And that's going to be kind of weird until we see it. But that's your shortcut. If it's a hole, it's going to be something that cancels if it's on top and bottom. Now for this example, x plus 1, I can't factor. X plus 2, I can't factor. So this is as simple as it gets, and nothing cancels top and bottom. So for this one, there are no holes. All right, so let's come here, and all you have to do is say no hole, if that's the case. All right, so we got 3 examples, and I try to come up with examples that are going to kind of cover all of our possibilities here. So let's start. All right, so for our first one, I've got x plus 2 over x squared minus 4x plus 30 or minus 32. Okay, so the first thing I'm going to do is I'm going to go ahead and factor, right? Just because I know I'm going to have to do this every single time. X plus 2 can't be factored. That's as simple as that one gets. X squared minus 4x minus 32 is a plain Jane trinomial. So I want to find 2 numbers that multiply to negative 32, but add to negative 4, right? And that's going to be 4 and 8, and I need 1 positive, 1 negative because of this negative 32. Bigger number keeps the sign in the middle. So that means that the 8 keeps the negative, and the 4 gets a positive. All right? So I'm going to kind of go in order. First thing we got to find is our x-intercept. All right, my shortcut for the x-intercept is to set the numerator equal to 0. All right, numerator equal to 0. So for this problem, I have x plus 2 equals 0. Then I solve. So I subtract 2. So we get x equals negative 2. So that's my x-intercept. Now, if it's an x-intercept, I need to write it as an ordered pair. So that means it's on my x-axis and y is 0. So my ordered pair is negative 2, 0. So there's my x-intercept. Okay, my y-intercept. My shortcut for the y-intercept is to divide the constants. You got to keep the C words in the right spot. So this is dividing the constants. So that means I'm going to go back to the non-factored one. Right? I'm going to come back over here to the one that we didn't factor, the original. And I'm going to ignore everything. So I can ignore all of these, right? And just look at my constants. Okay, so my constants are 2 and negative 32. Right? So that means I have 2 over negative 32, which I can simplify. Stays negative, but 2 goes into both of those, and we get negative 1 over 16. All right, and just like before, it has to be an ordered pair. So my ordered pair for my y-intercept has a 0 first, and then negative 1 over 16. All right, so I numerator equal to 0, and then my y value is 0 for the x-intercept. I divide the constants, and my x value is equal to 0 for the y-intercept every single time. Okay. Vertical asymptote, and I'm going to abbreviate with VA. Right, so your vertical asymptote shortcut is to set your denominator equal to 0. Right, now if I'm saying the denominator equal to 0, let's use the factored version, right? Because the factored form will help you solve a lot quicker, because if I started back here, I'd have to factor it to be able to solve it. So if I'm setting something equal to 0, use the factored form. It makes it easier for you. So then we have x minus 8 times x plus 4 equals 0. All All right, so that means I have two options. X minus 8 can be 0. X plus 4 can be 0. Add the 8, and we get x equals 8. Subtract the 4, and we get x equals negative 4. All right, you leave your vertical asymptotes as x equals, right? Because that's how you write the equation for a vertical line. So my answer, I have two answers, x equals 8, x equals negative 4. All right, for horizontal asymptote, we got to turn to our buddy Bobo. Okay, it's either going to be Bobo, Botan, or Spud. Okay, so if I come back to this one, I got to go back to my original problem, right? Because this is where I'm going to see what my powers are. So I have a first degree up top and a second degree on the bottom. So that means for this example, it's bigger on the bottom, right? Because I have a 2 on the bottom and a 1 on the top. So bigger on bottom means that my asymptote is 0. That's the O in Bobo. Right, and it's always y equals for a horizontal asymptote. All right, and then our last one that we're looking at is looking for any holes, right? And remember, your hole comes if anything cancels. So way back in the beginning, right, we factored this out and we said there is x minus 8, x plus 4 on the bottom. Nothing is the same on top and bottom. Nothing cancels. So that means there's no hole. All right, so my answers, my x-intercept is at negative 2, 0. My y-intercept is at 0, negative 1 over 16. My vertical asymptotes, I have 2 at 8 and negative 4. And then my horizontal asymptote is at 0, and then there's no hole. So those are the 5 things we're looking for right now. And the more you do it, the quicker it's going to get because it's the same steps every single time. All right, so we got 3 examples, 2 more. All right, so for the next one, first thing we're going to do is we're going to go ahead and factor if we can. So for this one, x plus 5, I can't do anything with. Right, and then I have x squared plus 1. Okay, so I have 2 terms. Remember, if you have a binomial, the first thing we look for is a GCF, no GCF. Right, second thing, we can try difference of squares. So x squared is a perfect square, 1's a perfect square, but I don't have a difference. So it can't be difference of squares because it's addition. And my other option for 2 terms is the cube pattern. Okay, so 1's a perfect cube, but x squared is not. So that means I can't factor it. All right, so there's definitely nothing that cancels, right? So I'm going to go ahead and come down here. And we're going to say that there's no hole. Right off the bat, I know that there's no hole because nothing canceled. Okay, for the first thing, our x-intercept, all right, which I'll accent. All right, to find our x-intercept, I need to set my numerator equal to 0. So x plus 5 equals 0. Solve for x, and we get negative 5. All right, so I have one x-intercept at negative 5. All right, so my answer is negative 5, 0. All right, side note on the x and y intercepts. These are rational functions, right? Remember, in order to be a function, you need to pass a vertical line test, right? Which means you can't have dots on top of each other, right? Like if you had a function, right, it can't cross twice anytime you have a vertical line. You can only touch one time, right? So in order for that to happen, I can have a bunch of x-intercepts, right? Like this, right? This example here, this is a function, and I have multiple x-intercepts. But I can't have more than one y-intercept. Because if I did, right, if this function came back down and I crossed again, it no longer passes my vertical line test, right? So I can have multiple x-intercepts, but I can have at most one y-intercept. Now, you can have no x-intercepts and you can have no y-intercepts, right? But you have to have, you can't have more than one y-intercept. All right, so the next thing we find is our y-intercept. And to find our y-intercept, we divide our constants. So I go back to my original here. Well, or only 1 because we couldn't factor anything anyways. And I look just at my constants. So in the top, I have a 5, and on the bottom, I have a 1, and 5 over 1 is 5. And then we write your y-intercept as 0, 5. All right, vertical asymptotes, I work with the denominator. So I set my denominator equal to 0. And I try to solve. All right, so I can subtract the 1 over. But then I get x squared equals 1. So to get x by itself, I need to take my square root. But I can't take the square root of a negative. I get an imaginary number. So that means I don't have a negative or a 0 in the denominator. All right, so if that's the case, it's never undefined. So there's no vertical asymptote. All right, which if you think about, if I plug a positive or a negative number into x squared, it's going to end up as a positive number. So then if I take a positive number plus 1, I'm getting more positive, so I'm never going to be 0 in the denominator. All right, and then the last thing we got for this one is our horizontal asymptote, and we turn to Bobo, Bott, and Spud. So if I look at my exponents, the biggest exponent up top is a 1, and on the bottom is a 2. All right, so just like before, or sorry, not just like before, the opposite of before. All right, no, it is just like before. I'm losing my mind. All right, button, okay, this is none. All right, so for this one, we do not have a horizontal asymptote. So for this function, we don't have any asymptotes. We don't have a vertical, and we don't have a horizontal, and we don't have a whole. All right, for our last example, okay, the first thing we're going to do is factor, okay, because we want to see if anything cancels, and it's important that you cancel first, right? And you'll see why in just a second. So for this one, up top, I have a plain Jane trinomial, so I want to find numbers that multiply to a -6, right, but add to a +1. And I just realized something. Woo, going back to this problem. That is not bigger on top. I don't know what the heck I'm thinking. Okay, for this one, it's bigger on bottom, just like it was before, right? Because I got a 2 on the bottom. So for this one, all right, I do have an asymptote, and it's at y equals 0. My apologies for that. All right, bigger on bottom, so it's at y equals 0. All right, now back to this one. Okay, so up top, I want to multiply to a -6, but add to a 1. All right, so that's going to be 3 and 2, and I need 1 positive, 1 negative to get to a -6. And then I want to add to 1, so the bigger number stays positive. So that means I have an x plus 3 and an x minus 2. On the bottom, we have x squared minus 9, so we can do difference of squares. So that becomes x plus 3, x minus 3. And now for this one, something cancels. Right? So the something that cancels, right, is going to be our whole. So I'm going to come down here because that's normally our number 5. All right, so for this one, our whole has to do with this x plus 3 because that's what canceled. All right, now the reason that there's a whole there is because now that it cancels, when I simplify this, my new problem becomes just x plus 2 over x minus 3. All right, and then I'll start working through and finding, my x-intercept, my y-intercept, my vertical asymptote is going to have to do with this x minus 3, right? But that's it, because that's the only thing that's in the denominator. But my original problem had an x plus 3 down there too. So we still have to take into account that the original problem had a chance to be undefined when x plus 3 is 0. So that's still going to, be something where we divide by 0, and we cannot do that. So that's why we call it a whole. So to figure out the whole, I take whatever it was that canceled and set it equal to 0. And then we solve. So I subtract the 3. So I get x equals -3. That's my whole. All right, and we say the whole is at x equals -3. All right, so that ends up being my answer for the whole. all right? But that's different. Like, that doesn't affect the rest of the problem. Now, the rest of the problem, I go back and I'm going to use this guy to answer all my questions just like we've been doing. So to start with, we have an x-intercept, right? And that's setting the numerator equal to 0. So we say x plus 2 equals 0. Subtract 2, we got this negative 2 again, right? X-intercepts, we make y 0. So there's my x-intercept. Y-intercept, right? We go to my constants, the last number. So I'm going to divide my constant. So I have a negative 6. Oh, nope. Sure don't. A positive 2 over a negative 3. All right, and I can't simplify that. So that means that my y-intercept is going to be at 0, negative 2/3. All right. Okay, we're ignoring this original function now. Once we canceled and simplified, we go back to this guy, x plus 2 over x minus 3. All right, vertical asymptotes, we set the denominator equal to 0. So my new denominator is x minus 3. All right, add the 3. So I have a vertical asymptote at x equals 3. And then the last thing, our horizontal asymptote, right? And that's going to Bobo-Bottensput. So for this one, I have x to the first power over x to the first power. So they're the same, right? And so that's a spud. So same power, you divide, and we divide the coefficients, the numbers out front. So out in front of the top x is a 1. So that's y equals 1 over, and in front of the bottom x is another 1. And 1 over 1 is 1. All right, so I have a horizontal asymptote at y equals 1. Okay, so x-intercept, numerator equal to 0. Y-intercept, divide your constants. Vertical asymptote, denominator equal to 0. Horizontal asymptote, Bobo-Bottensput. And then your whole is only if something cancels in the very beginning when you factor and simplify. You always need to work with the simplest fraction when you start finding everything. So the first thing you always look for is to see if you can factor and if anything cancels. And if it does, that's when you have a whole, right? But if nothing cancels, there's no whole, all right? And that's it for our start to the rational functions. We'll look at graphing them and actually, putting them on our XY axis next.